Hello everyone. In the previous lecture, we have studied about lens. In this lecture, we will take up some derivations based on lens called as lens maker's formula and lens equation. So, the first formula is called as lens maker's formula. Now, this formula is true for any kind of a lens, and also we can derive the formula for any lens, but here we will derive it for a convex lens. So we'll consider a convex lens with an optic center called as C. Let the surrounding medium have a refractive index called as NS, just to indicate its surrounding medium refractive index, and also here it will be NS, and let the lens refractive index be called as NL. Let an object be placed at a point O. Now light from this object will fall on the first interface. Because of refraction, let's call this as A, B, D. So let the first face be called as ABD. Now light is moving from one medium to another medium, so light would refract, because of which light path would deviate, and in this case light would bend towards normal like this. If suppose another surface, which is if AED was not there, then light would have traveled like this. It would have traveled to some point called as I dash. So I dash is the point where we would have got an image So this point is where we would have got an image if the surface AED was not there. But because of refraction, since light is moving from lens to surrounding medium, the light again further refracts at the surface AED, and because of which light ray would bend away from normal, and so here, somewhere here, at this point, you get the image I. Now for the entire lens, O is the object and I is the image point. I dash would have been the image if the surface AED was not there. We know for a lens that optic center is a reference point. So in this case, CO is minus U by sign convention, CI is plus V. This is what is by sign convention. So lens maker's formula is a relationship between the refractive index of the lens and surrounding medium as well as the radius of curvature. So let's begin. So going forward, recall that an expression for spherical refracting surface is given as N2 by V minus N1 by U is equal to N2 minus N1 by R. Now with this in mind, we look at the first surface. The first surface for the surface A, B, D, somewhere here an object is placed. So light falls on this surface ABD, and the center of curvature for this first sphere is somewhere here. If we draw normal from this point, this would have been the normal from this point. So, to the center of curvature, the light ray would bend towards normal, and finally somewhere here we get the image, and this point would be I dash. Now let us use the spherical refracting formula in this case. Let's find what is N1, N2, UV and R. Here N1 is equal to the light originating medium, which is NS. It will be NS in this case, and here N2 would be the other medium, which is lens in this case. It becomes N for lens, and U here by sign convention would be, for the surface ABD, B would act like a pole. It will be minus of B into O, and here in this case V would be BI dash by sign convention, and R in this case would be BC1. Putting it back in the spherical refractive surface formula, what we get would be N2, which is N for lens, by V here is BI dash, minus N1 is N for surrounding medium by minus BO, that is equal to NL minus NS by R in this case is BC1. If you pull out the minus sign from minus BO, then this would become NL by BI dash plus NS by BO, that is equal to NL minus NS by BC1. Let's call it as equation number 1. We take second surface now. The second surface, I will draw it here itself. The second surface, it's like this. This is the surface, and this is the principal axis. This is point A, this is point E, this is point D. The light ray from the first surface was tending to go towards point I dash here. It's going towards point I dash, but because of refraction the light further bends and the image is finally obtained at the point I. Now for this surface, this is N for lens, this is N for surrounding medium. For the surface AED, E acts like the pole, and the center of curvature of this part would be somewhere here. We'll call it as C2. Now in this case, let us find what is N1, N2, U, V and R. Now keep in mind that for the surface AED, the image is formed at the point E. The image is formed at the point I as seen here. Now for the surface, where is the object is a question. The object cannot be O, because the object O was for the surface ABD, not for surface AED. So in this case, we assume that the image which was formed because of the first surface at point I dash, this acts like a virtual object for the surface AED. So in this case, N1 becomes, remember what was N1 told to you all? I told N1 means it is the light originating medium. Even though the virtual object is in the surrounding medium, where light is originating from the lens to surrounding medium. So here n1 becomes nl and n2 becomes ns. By sign convention, u is equal to ei dash and then v is equal to ei and then r here is equal to minus of ec2 by sign convention. I'll tell you why we're using sign convention here also. It become clear after derivation is done here. Putting it back, in the formula what you know is n2, which is in this case ns by v here is ei minus n1 here is n for lens by u would be ei dash, it is equal to ns minus nl by r, which is minus ec2. If you take minus n on outside from both the terms, then this would become, this becomes ns by ei minus nl by ei dash is equal to nl minus ns by ec2, called as 2. So we have two equations here. We have two equations 1 and 2. Now to understand that, the entire derivation is for thin lens. A thin lens would mean whose thickness is small compared with distances involved. It is not obvious here, but for very thin lens, the points B, the points E will be close to point C. So in equation number 1 and 2, replace points B and points E with point C, because as seen here, C is our reference point. So writing for thin lens, we replace points B and points E with point C. So we add 1 and 2. First we'll add the left hand terms. So it is nl by ci dash plus nl by co. Here it is this ns here, not n, it's ns here, plus ns by ei, this s here, ei minus nl by, okay, this e should be c, so ci minus ci dash, that is equal to, from the right hand terms, nl minus ns is common, that gives us nl minus ns. If that is taken as common, then 1 by bc1 we can write as cc1, and here plus 1 by cc2. This is what we get. From here, this term, this is cancelled. So what remains here is ns is common between these two terms. So ns comes out, get 1 by ci, get c over here, for the term over here, 1 by co plus 1 by ci, that is equal to, it will be nl minus ns 1 by cc1 plus 1 by cc2. Again look at the values. What is co? Co was minus u, cis plus v. So putting it back, what we get here is, we can bring this ns down to the right hand side. So minus 1 by u plus 1 by v is equal to nl minus ns by ns, that whole thing into 1 by cc1 would be plus r1, because cc1 would be the distance between optic center to the first center of curvature, which would be somewhere on this side. It's somewhere on this side. So by sign convention, that would be positive. and then CC2 will be negative, so minus 1 by R2. You can rewrite this as 1 by V minus 1 by U is equal to, if you make the terms here, it becomes NL by NS minus 1 into 1 by R1 minus 1 by R2. So this is the next equation. We can call it as question number 3. Now recall what was focus defined as. By definition, we define focus to define focus we took U tending to infinity. So if U tends to infinity, then the point where image is formed would be the focus itself, and in this case V becomes F. That is because, if you look at the case of a lens, if we look at parallel light rays, think of parallel rays, think of a ray from here. This ray after refraction will go somewhere here. So at this point we get the image. So this becomes the focus. Distance from here to here would be the focal length, but in this case distance between here to here will be V also. So V becomes F. So putting that here and writing in equation number 3, what we get is, we get 1 by F minus 1 by infinity is equal to NL by NS minus 1 into 1 by R1 minus 1 by R2. Now this term here, 1 by infinity, would be 0. Let's skip a step, we'll do directly here only. This is what we get. We call it as question number 4. Now compare 3 and 4, or you can put this value from here, and what we get here would be, putting it value, we get 1 by F is equal to NL by NS minus 1, 1 by R1 minus 1 by R2. So this is called as lens maker's formula. It's called as lens maker's formula. Now here, keep in mind that even though this equation was derived for a convex lens, the same equation could be derived in the concave lens also, and we can use this equation for any kind of a configuration of lens. Again, while using this formula, remember to use with sign convention. And observe here, for a convex lens. So for a convex lens, what we get is, we know for convex lens that R1 is positive and R2 is negative. We put it back here, we get 1 by F is equal to NL by NS minus 1 into 1 by R1 plus 1 by R2. This term here, the last term here, is always positive for convex lens. So for convex lens, as long as NL is more than NS, even this term also be positive. So what we get here is, we get 1 by focal length would be a positive term into a positive term, which means F becomes positive. So for a convex lens, as long as N for lens is more than N for surrounding, this becomes positive. For a concave lens, what you can do here is, for concave lens, R1 is negative and R2 is positive. Recall that the convex lens, the distance between the optic center to here, this would be R1, this would be R2. By sign convention, since light moves from left to right, R1 is negative and R2 is positive, which means what we get here is 1 by F is equal to NL by NS minus 1. It's 1 by R1 minus 1 by R2. From here we take R minus sign common. That becomes minus of NL by NS minus 1, 1 by R1 plus 1 by R2. So here, again here also it's 1 by focal length. So as long as N for L is more than N for S, anyway this term is positive, this also is positive, but there's a minus sign outside here. So as long as N for lens is more than N for surrounding, the focal length of a concave lens would be negative because of this minus sign here. So F is negative. For example, think of lens kept in air. In that case, N for lens would be 1.5 because lens is made of glass mostly. N for surrounding would be 1. That is the reason that a convex lens behaves like a converging lens because of this factor here where F is positive. And then a concave lens behaves like a diverging lens because F is negative. Recall that we studied if F is positive, it means it is a converging lens. F is negative means it's a diverging lens. Now comes something very interesting. Suppose imagine that if N for lens is less than N for surrounding, then what will happen is, in that case, for a convex lens, we get 1 by F is equal to NL by NS minus 1 into 1 by R1 plus 1 by R2. Anyway, this term will be positive, but this term becomes negative. For example, think of lens placed in a medium of refractive index 2. Then this becomes 1.5 by 2 minus 1. That becomes minus 0.5 by 2. So this term becomes negative. So finally F becomes negative. If we do same thing for a concave lens, then what happens in this case? F becomes positive. So what is seen here is that when a given lens is placed in a medium of higher refractive index than the lens itself, they'll have different properties. That is, a convex lens will have negative focal length, which means a convex lens will behave like a converging lens. Will behave like a diverging lens because F is negative, and a concave lens will behave like a converging lens. So their behavior is interchanged. So as long as N for lens, that is refractive index of lens, is less than that of surrounding, is more than that of surrounding medium, they'll have usual property. When the refractive index of lens is less than that of surrounding medium, they'll have different properties. We can have a case where both R1 and R2 are equal. So if R1 and R2 are equal, in that case, if it is a convex lens, it is called as equiconvex lens. It is called as equiconvex lens. And if it is a concave lens, it is called as equiconcave. So even this could be asked numericals. It is equiconcave lens. Do remember that if you put R1 and R2 directly here, the answer would be wrong because it would become then wrong value. So in that case, keep in mind that to use sign convention. It's very, very important. Now comparing 3 and 4, basically these two are same only. So these two are same only. Now compare 3 and 4. If we compare 3 and 4, then what is visible here is, look at left hand side and right hand side. The right hand side has a term which is same as given here. So comparing 3 and 4, comparing 3 and 4, what we get is, we get 1 by f is 1 by v is equal to 1 by v minus 1 by u. This is called as Lens equation. We call it as 5. This is called as Lens equation or Lens formula. Now Lens equation is a relationship between u, v and f, while Lensmaker's formula is an equation between refractive indices and radial curvature. So you can think of this equation something like f is equal to r by 2 for spherical mirrors, and we can think of this something analog to 1 by f is equal to 1 by u plus 1 by v. So these are analog equations in case of spherical mirrors. The next topic is called as linear magnification. We have studied this topic earlier also, and just to recap it, linear magnification is defined as ratio of linear size of the image to linear size of the object. It is given as hi by ho, where hi indicates linear size of the object and ho indicates linear size of the, hi indicates linear size of the image and ho indicates linear size of the object. So this is definition of linear magnification. Solve it and see in case of any lens, then what we get here as seen here, we take a case where we get a condition where an object is placed in front of the lens like this. We will call this as point A and point B, and if we draw the light rays, so you have learned in school as to how to find the image for different positions of the object. Just go through it in case you're not able to recall it. For some position, imagine that the image formed here would be, say, inverted. It's inverted like this. In this case, if you use the ray diagrams, this is what you get, something like this. This is what we get here. This is what we get. This is one light ray. This is what we get from here. We can prove by geometry that if you call this as point C, and this is point A dash, this is point B dash, then by geometry we can prove that these two triangles are similar triangles. That is because this angle is equal to this angle, and also the angle made here is same as the angle made here, because the object and image are always correct. So that would leave us with these two angles being equal. So by property of AAA, we can tell that triangles ABC, that is triangles ABC and triangle A dash B dash C are similar triangles. That would mean that the ratio of sides are proportional. So AB by A dash B dash is equal to BC by B dash C, that is equal to AC by A dash C. So here we have three different equations in one equation form. So out of these three, we'll take any one relationship. As we saw in case of spherical mirrors, we drop the term which contains the hypotenuse. So we drop this term, and what remains here would be AB by A dash B dash is equal to BC by B dash C. Now AB would be height of the object and A dash B dash is height of the image. When we put it back here, then what we get would be AB, which is height of the object, by A dash B dash, which is minus HI by sign convention. It is equal to BC would be U, that is minus U by sign convention, because distance between C to B would be minus U, and then distance between C to B dash would be plus V. From here, this minus gets cancelled, and if we take the LCM, if we take reciprocal of each terms or take inverse of it, then HI by HO is equal to V by U. Therefore, what we get from here is M is equal to V by U. Now recall that for a spherical mirror, we had M is equal to minus V by U. This was for a spherical mirror. Observe these formulas carefully, because as I told you, in case of optics, the formulas are straightforward, so except with sign conventions. So be careful with the terms. Again here, if M is say negative, it means it's a real image, and if M is positive, it means it's a virtual image. Let us understand that. Think of a case where we have a lens and somewhere here we place an object we call as A and then B, and somewhere here we get an image we call as A dash B dash. We put it back here in the equation, then what M would be is equal to, if you look at this, in this case both U and V are negative, it becomes minus V by minus U, which becomes just V by U. So it basically means M is positive. So positive means a virtual object. Again, M could be equal to 0, M less than 1, M equal to 1, M more than 1, and M tends to infinity. So these are the possible values of M. Thank you.